Imax, that is 192 watts. Alright, let's now talk about capacitors in AC circuits. Now remember, a current flows through a capacitor only when the voltage across changes. When the voltage remains steady across the capacitor, the current does not flow. Well, that is very important in this case. Whereas resistors allow a flow of electrons through them directly proportional to the voltage drop, capacitors oppose change in voltage by drawing or supplying current as they charge or discharge. You see, a current flows through a capacitor only when they get charged or discharged. As they get charged, the potential difference across the capacitor changes, and the current flows only when the potential difference changes. When the capacitor is fully charged, it has a constant potential. There will be no current flowing in the capacitor. Now here I have a diagram of an AC generator connected to a capacitor of capacitance C. Now, the flow of electrons through a capacitor is directly proportional to the rate of change of voltage. You see, when the voltage is steady, there is no flow of charges into a capacitor. So, the flow of electrons through a capacitor is directly proportional to the rate of change of voltage across the capacitor. Now, the current through the capacitor is a reaction against the change in voltage. Only a change in voltage will produce a current in the capacitor. I want you to watch these two drawings. Now, the blue drawings is the voltage across the capacitor, and the red, I don't think it shows as red in the broken lines. Now, look at the slope of the blue line. The slope is maximum here, the slope reduces and becomes zero. So the rate of change of voltage is maximum. That means that is when the current is maximum. And when the voltage is peaked, the rate of change of voltage is zero. That is when the current is zero. Alright. So the instantaneous current is zero whenever the instantaneous voltage is at a peak, and instantaneous current is at a peak whenever the voltage is changing at the maximum rate. So you must now understand this. Now see how a phase difference comes about between voltage and current. Now this results in a voltage wave that is minus 90 degrees out of phase with the current. You can see when the current is a maximum, the voltage is zero. So we say that current is ahead of the voltage by 90 degrees. There you are. The current is ahead of the voltage by 90 degrees. That's the representation. We say the voltage lags behind. Voltage lags behind the current by 90 degrees. Now, since the voltage and current are 90 degrees out of phase, the capacitor offers a reactance represented by XC. Now, a capacitor's opposition to change in voltage translates to an opposition to an alternating voltage in general. Well, I'm not going to go into the details. Now, the reactance of the capacitor is expressed in ohms as we normally do, and is symbolized X sub C. And I want you to remember this. The value of the capacitive reactance is 1 over 2 pi Fc, where F is the frequency of the AC. Now look at this. The reactance of a capacitor is inversely proportional to the frequency of the AC. All the other quantities are constant there. So take note of that equation. The reactance of a capacitor X sub C is 1 over 2 pi Fc. Let's do another example. Calculate the reactance and the current in the circuit shown. Here we have an alternating current source which produces a 10 volt EMF at a frequency of 60 Hz connected to a 100 microfarad capacitor. So we got the capacitance, we got the frequency, therefore the capacitive reactance X sub C is 1 over 2 pi Fc. We know all those values. That gives you the reactance 26.53 ohms. In that case, what is the current? The current in the capacitance is Vc divided by Xc, voltage across the capacitance divided by reactance of the capacitance. And that will be 0.38 ampere. You can see all these are very simple, straightforward, one-step problems. Now, however, we need to keep in mind that the voltage and current are not in phase. The voltage lags behind the current, or we can say the current leads the voltage by 90 degrees. You can see here, if this is the current, that is the voltage. The current leads by 90 degrees. And this is the reactance of the capacitor. Another example. A 20 microfarad capacitor is placed across a generator that has a maximum EMF of 100 volt. That is the Emax. Find the capacitive reactance and the maximum current when the frequency is 60 Hz. We'll always start by picking the data and then, of course, looking at the relevant equation. The capacitive reactance X of C is 1 over 2 pi Fc, where we know the frequency is 60 Hz and the capacitance is 20 microfarad. Use them in proper units, and that gives you the reactance is 132.6 ohms. Now, the maximum current is maximum voltage divided by the reactance. You can see the same situation, Ohm's law, I equal to V over R. In this case, it is not R, but reactance. And we know all these values. So the maximum current is 0.75 ampere. All right.